I am recording. Excellent. Now, folks, when Simba is presenting, he's going to be saying amazing things. And you're probably going to think to yourself, I have questions, either at the beginning or the middle or the end, or maybe when someone asks an amazing question. Want to let you know, there's a little option at the bottom of your screen. It is a Q&A box. Any questions you type into the Q&A box, he will be able to see those and answer them in real time. We are going to start Q&A at 12:50 p.m., which gives us about 10 minutes. So here we go. So Simba, thank you so much for joining today. You obviously have an amazing background. So thank you so much also for making the time. Know you're busy. So you are the co-founder and CEO of StreamSQL. You have been building machine learning systems on huge, massive data sets for years. And today you're going to be talking about StreamSQL Feature Store and why you chose to build it on top of Apache Pulsar. So without any further ado, I'm going to mute myself and let you share the magic.
Yeah, hi everyone. Today I'm going to be talking all about feature stores. I'll be describing what they are, why we built one and why we needed one, and why we decided to build it on top of Apache Pulsar. So I'm Simba, the co-founder and CEO of StreamSQL.io. So StreamSQL is a feature store, but we actually built it internally at my last company. And the whole point was to, it was a feature store, and we actually were built on top of Apache Pulsar. And at our peak, we're handling over 100 million monthly active users. Feature stores kind of fit in this weird in-between spot between machine learning and data engineering. It's almost like ML engineering. It's like kind of a new field that's still being figured out. So I'll begin by talking about the ML process generally, like what it was like on our machine learning teams, how our day-to-day went, how we built and iterated on our models. I'll then jump into the data engineering side. I will talk about how we built our ML pipelines and why we moved them over to Pulsar. And then finally, I'll end by talking about feature stores and why we built ours and how we built ours on top of Pulsar. And like I said, I'll leave 10 minutes at the end for Q&A. So machine learning, hot topic, obviously. In a nutshell, you can break it down as a machine learning model is just a function that takes input features and generates an output. Now, before I go any further, I'm going to use the word features a lot. It means feature store. A feature in machine learning has nothing to do with a product feature. A feature is another word, you can think of as another word for an input to a model. So models take inputs, those inputs are called features, input features. In this case, we have a model. So this is like something we would have built at our last company, a personalization model that would recommend the next article for a user. And to do that, our input features would be the last 5 articles they read, the current article they're reading, average content length, diversity of our reading taste, etc. So we'd feed them to a model and it would recommend the next article. So a lot of people, when they think about like what a data science or a machine learning data scientist does, they think of that picture on the left. It's like a lot of math, it's almost like that Coursera course that most people start doing machine learning with, where you learn about like backpropagation and simple models. In reality, not that much time is spent at that layer, the math layer. A lot of time is actually spent in the higher level layers. And think of it almost like, when you're learning computer science, you might learn a lot about like a red-black tree, how to implement one, how they work, all the mathematical proofs for one. In reality, like when you're actually, it's important to understand, but when you're applying this stuff, you just import some library someone wrote to use it. You don't build it from scratch. Same thing applies to machine learning. You can, for example, import a model, you can configure it and work that way. So since we're not spending time on model research, what do we do? Most of our time is actually spent on the data side. Part of that is data cleaning, getting our data together. And a lot of that is also on feature engineering. What that means is essentially like behind every model is this set of features. And the easiest way to make your model better is not to focus on like getting the new cutting edge model architecture in there. likely you can have huge jumps in performance by adding new input features. We actually found that our biggest gains almost always came from feature engineering, not from model development. For example, I'll give you a simple use case of that. We had a model that would predict if a user was going to subscribe based on like what they were reading. We found that if you added a feature, which was the user agent, so essentially like what device is the user on, it really, really enhanced how powerful that model was. And the reason was kind of simple in retrospect. If someone's on a brand new iPhone, that means they probably have more discretionary income. It says a lot about the user that the model can deduce. And if they're on, an Android phone that's 10 years old. So using that kind of stuff and doing that sort of feature engineering is how we cause most improvements to our models. So to really like hammer it in, for our machine learning process, the models were not the hard part. It wasn't where we spent most of our time. It was actually building and maintaining the data pipelines. And it's not unique to us. This is actually a slide I cut from the Microsoft Azure sales deck. It's recommended architecture to build a machine learning solution. As you'll notice here, the majority of the stuff like Azure Events Hub, Data Factory, Kubernetes, et cetera, are kind of tangential to machine learning. Think of the model as just like a CPU. CPU, super powerful, like probably one of the most expensive parts by square inch in your computer. But without the motherboard and all the pieces around it, it's not really that useful. And most of the time is actually spent building all the tooling around it, all the data infrastructure around it. In our case, our teams were spending over 80% of their time building and maintaining machine learning pipelines for feature generation, as opposed to working on the model side. So my goal was to shorten that time and like make sure that we were being efficient there. That was clearly the highest priority bit. So my focus became, how do I allow us to do better there? So in that 80% of time, they were feature engineering. And this is kind of the cycle. It's this kind of a cyclical thing. You come up with an idea. I think that the diversity of the content a user reads would help us predict what to recommend. I would generate a training data set from that. I would validate that it works. So I would like train it offline, validate an offline data set, and then I'd deploy into production. And then I would restart again with a new idea. So this was the feature engineering cycle that most of the time was getting spent on. Now, there are two things that you have to generate in this feature engineering cycle. There's a training data and online features. So when I need to make a recommendation, I would get the user ID. I wouldn't get the whole feature set. So the feature set is the thing on the left here. I wouldn't get that from the API call. I would get a user ID to the system. The user ID would then be mapped to the features that would be stored in kind of a storage online, like in Redis, that would return the set of features. And then that would make a recommendation. I'd also have to create a training data set. And for the training data set, I would have tuples of feature sets and what actually happened. So like the model has an output, but there's an actual result, like what it should have, the right answer per se. And that's what you need to train. So let's dig into how those two were generated in the original system. Originally, we would use, all of our events would come in, we store it in like S3, and we would use Apache Spark to work on it in batch and generate a training data set. The gotcha with training data sets is you have to generate point-in-time correct training data. What that means is, for example, for each read event, I want to predict, hey, this is what the user is going to read next. So I would take what they read next, and I would generate the feature set at that point in time. I needed to be at the point in time of the read because that's what the model would have actually been given in a production system. So to generate training data set, you kind of have to go back in time and generate the features at each of those individual observations. And so again, it makes the queries and the jobs much more complicated, but it's not insurmountable. In the perfect world, We did the exact same thing on streaming, right? Like we could go and we have these, let's say we're using Kafka. And we used to use Kafka before we moved to Pulsar. We'd have these events come in, we'd process them with Flink, and then we'd store them into Redis. And Flink can do all the same things of doing windows and handling building and generating stateful features. The problem is, when a Flink job runs, it starts at that point in time, at those events. That means that all these stateful features, like the last 5 articles read, would be originally set to null, or to an empty array in this case, because we would not have bootstrapped any data. We would just start that job at that point, that stream processing. What we would like to do, since we have all this data stored historically, we'd want to bootstrap these features. When we want to create a new feature, we want to process maybe the last 3 months of data to generate the features as they would be at that point in time, so that when we test that feature, we can have a strong representation of how it would behave in production. Here's how we used to do it. So let's look at, again, we're going to use total time spent reading per user as an example. This is how we would start by bootstrapping. We would start by processing past events in S3 using Spark. It would essentially look like that query at the top, like we just group by user and take a sum of all the read time and store that in Redis. The thing is that not all events will have been persisted in S3. So we will pass a message ID specifying the last event that Spark processed. So this is kind of how it looks. You have these events coming in. They're coming in, and let's just say they're ordered in time, and they will eventually be persisted in S3. There's some delay there. So Spark will crunch through everything in S3 up to the last event, and then pass the message ID of that last event. Now we still want to process all the events that came after that. Luckily, Kafka and Pulsar have this idea of retention period. You can set, usually in Kafka, at least I've seen it set usually around a week or maybe even a month. And it's not on S3 yet, but it is in Kafka, so it can be processed. And we can actually tell Flink to roll back to that message ID and then process from then on and get Redis bootstrapped up to date so that we have the current state of the features in Redis. And then we can just leave it running so that it continues to process events as they come in. So here's the whole thing. If that looks super complicated and like a headache to maintain, you'd be right. It was awful. And I'm not even talking about all the things that could go wrong. Like what happens if the Flink and Spark job are different? What happens if Spark or Flink goes down at a certain point? There's all these edge cases that I won't go into in this talk, but this was a nightmare to maintain. It would break all the time. It was so finicky. It kind of felt like this comic. It's this idea of like everything kind of felt like a house of cards. Like we had all these scripts and things were all automated, and it felt like it was like kind of working, but it was always felt like house of cards. It always like things would break, and when they'd break spectacularly. So if you look at it again, there's 2 parts. There's like the S3 to Spark batch processor, Kafka to Flink streaming processor. We had this idea of like, how can we merge those together? And we had the idea of treating the event log as an immutable ledger. What that means is that, think of it like a stack. It's like every event that comes in, we just add it onto the end of the stack. And the stack's immutable. You can't pop anything off. You can't change the order of anything. When it's written forever. The cool thing here is if I take that ledger and just pause it and copy it, it looks like a batch problem. Like it looks like something that a batch processor could handle, whether that be Spark or Flink in batch mode. If you read it event by event or only read at the end of the ledger, it looks like a streaming problem. So it gives us the right abstraction to be able to conjoin those 2 pipelines. And so how we did it in practice is we just turned on infinite retention of Pulsar. And so now all these topics in Pulsar were actually infinitely retained event streams. They're immutable ledgers. And now to bootstrap features, if we want to create a new feature, we'd write one Flink job, start it at the beginning of the stream or wherever in the stream we needed it to start. And Flink would handle getting it up to date and then processing features from then on. So all this complexity of passing message IDs, turning things on and off, etc., all went away. It also created a much more stable system because way less things can go wrong. It's a way simpler architecture than what we had before, which was this. So some of you might be thinking that Kafka also has infinite retention. Why not use Kafka? We actually tried to originally, and it didn't work for a variety of reasons, which I'll get into. One thing that Pulsar does really well is it has this idea of offloading. That means that with an immutable ledger, the ledger grows forever. So your storage capacity has to continue to increase forever, whereas it doesn't never get smaller. With Pulsar, you can offload segments of a topic. So you're writing to a Pulsar topic. Pulsar internally will break that topic up into segments, and those segments can be offloaded into cold storage, which can be S3, Google Cloud Storage, HDFS, etc. And now it becomes tractable to actually be able to store every event forever. When doing this in Kafka, you can't do that. So you actually have to continuously add new nodes and more storage capacity constantly, which ruins a majority of things. One, adding new nodes is an expensive operation in Kafka. Two, it's just expensive to keep things on disk. It's way cheaper and way easier for us to just put things into S3 or Google Cloud Storage or whatever else. So this was a huge win for us for using Pulsar. The other thing is scalability. Pulsar is built with a tiered architecture. So they have the broker layer, which is the Pulsar layer. They have the bookkeeper layer. The Pulsar brokers are stateless. They take events that the producer generates. A consumer can ask a broker for events, in which case the broker may just have it cached, as it will try to do that because that's kind of like the short path it's trying to optimize for. Most of the time, you're not going back into old segments. Most of the time, you're just reading from the head and continuously updating with a stream. And that when you generate a feature engineering, when you're feature engineering and you're going back in time and processing all the events, then the broker will go into Bookie and the bookkeepers. The cool thing is that both of these things scale independently of each other. So if we had a huge spike in the amount of streaming data we had coming in, we could just quickly add more brokers. They're stateless, super cheap to add and scale up and down. Bookkeeper is a little more expensive to scale up and down, but you can do it. But we could decide how to do that based on how much feature work was being done. So this allowed us to scale and more elastically cover our use cases better. So it's a better architecture, in our opinion. So this is cool and all. And obviously that architecture, the ML pipeline was way more powerful, way simpler. It just had one Flink job you could write and run, and you could run across your immutable ledger to generate features. It's event sourcing, which I'm sure a lot of other talks have talked about already. But it's the idea that your features are just materialized views of your events. Your events are your source of truth. And you can keep them as an immutable layer, but you keep appending to. The thing is, for machine learning, it turned out once we did that, we dramatically decreased our feature engineering time, or the cycle, the speed of that cycle was way faster. The thing was, though, that it still was the wrong level of abstraction for machine learning in particular. We started to see features as the building blocks of machine learning models. It was one thing that can be shared across multiple models. Multiple team members can be working on different features for the same model. But currently, we develop them and maintain them in ad hoc ways. They didn't have a dedicated system of management. To be concrete, that means that one, feature logic, so like how we generate the features, was split up across a ton of Flink jobs. It was not it wasn't one place, one source of truth of this is the feature, this is how it's defined, this is the definition of it. Two is there's no feature versioning and rollback. I mean, you can use Git to do some sort of stuff, but things were pretty ad hoc. You just run new jobs in Flink. There wasn't really a clear way to manage the features. Because there was no versioning and everything was so ad hoc, the idea of reusing features across models, sharing features across teams, discovering features didn't really exist. It was way too risky because everything was so ad hoc. And finally, like there's no integrations in TensorFlow, Jupyter, all these things that you would expect to use as a data scientist. It's, again, the wrong level of abstraction. It's a data engineering architecture, not a machine learning architecture. So the idea was to build on top. But I guess before I go into that, what we wanted was like a platform on top of the machine learning pipeline that allowed for features to be easily defined and shared, to have like almost like a registry of features. The thing is that, you know, we're learning as, I guess, like data scientists, we're learning how to implement the right process so that we can all work together and work faster. It's almost like with software engineering, like everyone's always talking about new agile workflows or new, you know, new CI/CD architectures or whatever. Data science has way more to learn still. Right now on the data science team, it feels like kind of a pack of wolves. Like everyone has their own task that they take on. They build their own features, they build their own models, they maintain their own stuff. There's very little stuff shared beyond just ideas across team members. What we want is kind of like these rowers. Like we want everyone to be working together on a single platform so everyone benefits, the whole organization benefits from everyone's work. And a feature store actually gave us that ability. Let's go back to this example. One of the features here is diversity of reading tastes. So that could be used to recommend the next article. It could also be used to predict if a user is going to subscribe, or to predict how often to send a user a marketing email. So by building this feature and modeling it, I can now share it across different models, and by creating a single feature, I've actually enhanced the performance of all machine learning models across my organization. And that's really where like the power came in of the feature store. It was a new way to think about features. They became kind of a first-class piece of the machine learning workflow, the machine learning process, rather than something you just generate using lots of pipelines. So again, the feature store, we've externalized it as StreamSQL.io. The whole goal of it was to accelerate and enhance machine learning development. And it does it, the feature store does it in 4 ways. One is it facilitates model development by allowing for that discovery and reuse and sharing. All of a sudden, there becomes this idea of a feature registry where you can search features, you can share them across teams, everyone can build and version on top of them. It becomes a new way to work together. Since there's a single feature definition and it just exists in one place and it's kind of declarative, you can deploy with confidence. It will be used to generate your training data and this, the production online data. That means that you know that the feature you will get will look the same in both contexts. You can deploy with confidence. Again, like we talked a lot about how we unify streaming and batch processing, but that's a huge value prop of it. And finally, we start to think about features as a building block for machine learning. Rather than treating features as kind of like just something, an input, they became building blocks. All of a sudden, you could reuse them across teams, but you could also use them across literally organizations or across completely different companies. For example, it's very common nowadays to use pre-built text embeddings. Like Google releases all these text embeddings that they generate themselves on their own data that people use. Now you can just import those and just use them. A lot of people will use third-party data sets like Weather data, and then they'll build ETLs on them and they'll build features for them. Well, now it becomes as easy as a click of a button to ingest those and start using and benefiting from those sort of third-party features. So I'm going to go into, so I'm just running the Q&A real quick before I go into this example. So, for instance, team, can we use start from Yes. So one is like how do you use it across different like platforms? If you're using TensorFlow in some places, if you're using Spark for ML in other places, the features. Data scientists don't like working on as a data scientist, I prefer to get a file with all my data. I don't like working with APIs because I have way more control if I own the whole file. So when we generate training features, we actually generate them in such a way that it's a file. It's literally in S3, and it's a Parquet by default, but you can choose how you want to export it, and you can work on that. So we purposely, we think a feature source should stop where the model starts. So you just do the features and no more. And then you just export those features in every single kind of way possible, just kind of connect it wherever is needed. That's how we think of that piece in particular. And then, so features are stored in Redis. So they are pre-processed. You don't want to be processing features on the fly. For example, like in this example, if I want to look at total time spent reading per user, I want to have that constantly being processed. So even though those events, the raw events, are coming into Pulsar, being kept there, they'll be processed by Flink, and then Flink will store that into Redis. And Redis will contain the pre-processed features. So it's kind of like a materialized view of your event stream. And those are what get used. So that's like your online features. Your offline features are, again, just like a file, a Parquet file or something. So I'll go into a fraud detection example. So I'll use the StreamSQL syntax, but this kind of applies to feature stores everywhere. For example, a lot of the stuff that a lot of our design decisions mirror Airbnb's feature store, which is called Zipline, which they've spoken about at depth. So this kind of applies broadly, but it kind of gives you an idea of how feature stores fit into the machine learning workflow. So there's 4 steps. First step is just connect and upload data. So in this case, like you might have a CSV of all your items. So let's say this example is fraud detection. So you have your items, which might include price, description, name, etc. in a CSV. You will have a stream. Let's say you're using Kafka still, and it will be a message, or it will be messages in JSON that will be received on the purchases topic. So you can upload and connect that to us as well, or to a feature store as well. So in my opinion, Flink, working at the Flink layer and like the data, like that data layer is not the right level of abstraction for a data science or machine learning team. It makes way more sense to work in SQL or work at a higher level language. And so feature stores allow for that. So for example, in this case, the SQL is this is generating the average purchase price per user. So we're taking purchases, which is a Kafka stream, as you'll remember. We're joining it with catalog, which is actually a CSV file. And we're using that to calculate the average purchase price per user. And you can just do this in SQL. You don't have to think about how everything gets done. Because of how we maintain all events, even if you connect Kafka, we'll actually store all historical events from Kafka. So this table will be materialized across every event we've ever received from Kafka by default. And it will continue to be updated. It's like a materialized view. It will continue to be updated as new events come into Kafka. There's all these common feature engineering techniques. One example is if you have a feature, let's say like price, the range of price can be really wide. Machine learning models can be really finicky when you have you have lots of null values, you have lots of features that have very different ranges. So it's very common to want to normalize them to fit in one general look. So one thing you can do here is say, hey, I'm creating a new feature. It's called average or square root of average purchase price. This is version 1. if there's a null value, I want you to set it to the median. So in machine learning, this makes sense because if you have a null value and you put a 0 to a model, it can output garbage. There's always examples of models like cancer detection models that work really well. But if you give it a picture of like a cat, it will say, oh, this is cancer. And that's just because models work well if you're in their bounds. If you go out of the bounds of like lots of null values or like huge outliers, they misbehave, famously. You can run operation like a square root operation on it just to like change the distribution of the data. You can truncate things that are more than 2 standard deviations away, etc. So this gives you a much cleaner way to define your features. And once you define them like this, they exist in the feature registry. They become searchable. Other people can use it. The version is immutable. So you can, if you depend on this version, you won't have to worry about someone breaking it under you. And you can start serving it online in real time. So after you register it, you can say, hey, give me the current value of that feature for this user. And you can get that. Finally, we talked earlier about generating training data. So again, when you generate training data, you have these events come in, like let's say it's like a read event. You need to generate features at that point in time of the read event. Now, before we would write jobs that would do all this logic. With a feature store, you kind of declaratively define where everything is. So you might say, hey, like I have a label, like, is it fraud? I have a timestamp. I have the user ID. Given that, and given a set of features, StreamSQL will automatically go through this, parse out the label, generate the features at that point in time, and generate it into a training file for you. And then you can pull it there. We optimize for making it really easy to add features and remove features from the training set. Everything's optimized per column. And that allows for us to easily be able to, again, iterate. Most of these features are also pre-processed. So we're not really generating the training data from scratch, running a huge job. It's cheaper for us to just keep it stored than to constantly keep regenerating the training data from scratch. Again, the goal is to take this feature engineering cycle, make it organized, like give it a piece of infrastructure and a process, like a feature store, feature registry, and also to give a, make it way faster for data scientists to think at a higher level of abstraction, define their features as they want to, maybe write some SQL if needed, and quickly go through the cycle. In our case, it let us iterate. Sometimes we would be working with teams, or if our data science team was larger than our entire team. And we would still be able to iterate faster on a larger data set. Again, we're handling over 100 million monthly active users, just because we had this feature store and it became such a core piece of how we worked. So StreamSQL, it's a feature store for machine learning. We're just entering beta. Again, it was an internal tool that we've decided to roll out in open source. If you're interested to learn more, or you have any questions about how we implemented, why we use Pulsar, etc., feel free to shoot me an email. It's simba@streamsql.io. And I'm a little early, but any questions?
Yeah, so I see we've got quite a few more questions in the Q&A box. And Simba, if I can just ask you, when you look at the questions, if you can just repeat them out loud for folks as well. I see we've got quite a few there. Yeah.
Cool.
And you got about 5 minutes, so take your time. We've got time. Yeah.
Cool. So do you have an architecture diagram for the feature store? I do. I'm going to come back to this layer because I have to pull it up. It's somewhere else, but I have it somewhere I can pull it pretty easily. And does StreamSQL feature definition language support Pulsar, or is it just Kafka for now? So the feature definition language is kind of agnostic. So again, like the feature store is a layer on top of this. Events come in, so you can connect them whether you're connecting via Kafka or Pulsar or whatever. We maintain our own Pulsar deployment. Everything you're looking here, you can't talk to our Pulsar directly. You can't talk to our Flink directly or our Redis directly. You go through the upload, transform, or query API. When you upload to Pulsar, Even, it doesn't, you can be upline from Kafka to Pulsar, you can be going from Pulsar to Pulsar, whatever, but internally we use Pulsar so that we can have an immutable source of truth. That gets pulled and processed through Flink, through our transform API. So when you write SQL in when you send a SQL transformation like this, we take this and then do a little bit of processing on it, and then essentially turn it into Flink SQL and pass it to Flink to actually do the heavy lifting for us. So it's, again, agnostic to that, which, again, lets our data scientists not worry about what our architecture is, but lets them think at a higher level. And lets us, again, leverage all the value that Pulsar gives us without them having to know how to use that themselves. And again, the features themselves are pre-processed and stored in Redis, so that when I have a recommendation come in, like here, someone asks me for a recommendation, I get a user ID and I pull the feature set from Redis, and I then can use that into the model to generate the output. Yeah, we do have StreamSQL from Pulsar. We do support Pulsar. And then how do these features work across different ML platforms? For instance, how do these features work across different ML platforms? For instance, my team might be using Spark for ML, while another team in my company could be using Cafe or something else. Can I share a feature between them? The answer is yes. Because we try to stop at the feature layer. So we stop at where your models start. We have some integrations, like for TensorFlow, just to make things a little simpler to bring them in. But our general API tries to be completely agnostic by not even worrying about what you're doing with the features. Some people actually generate features and then plug them into BI workflows, not even into machine learning. We don't really care. We're just generating the features for you. So it does work across Spark or Cafe or whatever else. We use it across Scikit and TensorFlow and Spark. Our features in the feature store stored in the Pulsar topic from Flink. What was a jump from customer Flink calls to the feature store location? So we talked about materializing a table, which I'll jump to. So in this case, we're using SQL to generate a table from a stream. We're technically joining a stream to a file to generate a table. You can actually materialize other streams. So for example, you could change this SQL so that you're essentially enriching a stream with a file, and that will plug back into Pulsar. A materialization, or a raw event stream, is we treat it the same way when we generate features. We don't see a difference. We kind of abstract it away. So you can generate new streams. A feature itself cannot be streaming, in the sense that a feature has to be some sort of lookup. When you have these this sort of thing, all of these things need to be concrete values, like the last 5 articles read. So that should be a lookup. You should be able to just give a user ID and get the last 5 articles read. So even if it's being generated from a stream, it is eventually the feature is pre-processed and at rest in Redis. And then, yeah, is there any more questions? Or if I didn't answer one of these questions well, feel free to re-ask or ask it in a way that a slightly different way maybe.
Yeah, folks, if you have any other questions, I do see another one just popped up. Got about another 2 to 3 minutes, so feel free to add more questions. Yeah.
Does the query API provide a background job to generate the features? Yeah, so when when you write a SQL query, we run a Flink job. And remember, our event stream, so in Pulsar, every topic has infinite retention. That means it maintains immutable list of every single event that's ever happened. So when we run the Flink job on it, it starts from the beginning, unless you choose a window. By default, it starts from the beginning, and it processes every event from the beginning to bootstrap the feature, and then continues to process it from there. So the Flink job runs forever. And then, yeah, and stores it into Redis.
All right. And just as a final closing here, Simba, can you just share again, where can folks reach out to you? If you can just throw out the slide, just is there a Twitter? Is connecting with you on LinkedIn okay? Kind of what's the best? Is email the best?
Yeah, so get me on email.
Okay.
I'm at Simba Khadder on Twitter. Feel free to follow. I post a little bit, but I definitely am pretty active on Twitter. I read a lot, but I don't write. Yeah, definitely add me on LinkedIn. Feel free to connect. Just mention that you saw my talk, and I would love to connect.
Awesome. Well, thank you so much. Before I stop recording here, I just wanted to clap for you because that was an awesome prezzo. StreamSQL, very exciting what you're doing there. So thank you so much for your time today.